Hello, we now continue with the notion of the rank of a matrix. The rank of a matrix is one of the most important topics in this whole course. So let us take an m cross n matrix, that is a matrix with m rows and n columns. Each column can be thought of as an element of Rm. So the columns of A is a bunch of vectors in Rn. And so I could take the columns of A and consider their linear span. That will be a vector subspace of Rn. This vector subspace is called the column space of A. Similarly, the rows of A can be regarded as elements of Rn, and I got a bunch of vectors in Rn. I can take their linear span, and this linear span is called the row space of A. So associated with any m cross n matrix, there is a column space of the matrix and there is a row space of that matrix. And so once you got these two vector subspaces of Rm and Rn respectively, you will ask, what are the dimensions? The dimension of the column space of A is called the column rank of A, and the dimension of the row space of A is called the row rank of A. Now, before we continue, I'm going to insert a small exercise here. Let S be a set of vectors. Let S be a set of vectors, and let linear span of S equal to V. Now this S may not be linearly independent. However, I can delete elements of S. If S is linearly independent, fine. If S is not linearly independent, what does it mean to say that S is not linearly independent? That means that one of the vectors can be expressed as a linear combination of the others. For example, if S contains vectors v1, v2, v3, and if v3 happens to be v1 plus v2, then when I take the linear span of S, v3 is redundant. Whatever I can get using v1, v2, v3, I can get with v1 and v2 alone. So if S is linearly dependent, then one of the vectors can be expressed as a linear combination of the others. And that vector can be dropped out of the list without affecting the linear span. In other words, I can shorten or I can make the set smaller. So there's a subset. I can delete a vector from S and get a smaller subset, say S naught, such that the linear span of S naught is again V. Now look at the smaller set S naught. If it is linearly independent, fine. If not, one of those vectors is a linear combination of the others, and delete that particular vector. Keep shortening or keep making this set smaller and smaller in such a way that every time the linear span is the same, but ultimately you will get a linearly independent set. So the exercise says, suppose S is a set of vectors such that the linear span of S is V. Show that by deleting elements of S if necessary, S contains a subset S naught, which is the basis of V. In fact, I given you the solution to this exercise. I just rattled off the solution of this exercise. In particular, you have taken the rows of a matrix and you have looked at the linear span of the rows. The rows themselves may not form a basis for the row space. The rows themselves may not be linearly independent, but by omitting some of these rows, you can get a smaller subset of rows that will serve as a basis for the row space of A. Similarly, you have taken all the columns and you looked at the column span. You have looked at the column span or the column space of A, the linear span of the columns, the vector subspace generated by the columns. The columns themselves may not be linearly independent; they could be linearly dependent. Namely, one of the columns maybe a linear combination of others. Delete that column and so retain a linearly independent subset of the columns that will span the column space. So you can always do that. And so you can get a basis. So among the rows, you can find a basis for the row space of A. Among the columns, you will find a basis for the column space of A. So you got this two vector spaces, the row space and the column space. The row space is a vector subspace of Rn, and the column space is a vector subspace of Rn. And the column rank of A is the dimension of the column space. So the column rank is obviously less than or equal to n, and the row rank is obviously less than or equal to n. But we are going to see a remarkable result. But before I state that remarkable result, we need a lemma. What is that lemma? You take a m cross n matrix A. Now, if you take an m cross n matrix, you may want to perform an elementary row operation. Now, an elementary row operation does not alter the column rank of A. Performing a row operation does not change the column rank of A. We will prove a more specific result. We will prove a more precise result. Suppose E is an elementary matrix. Remember, performing an elementary row operation on a matrix is equivalent to pre-multiplying the matrix by the corresponding elementary matrix. So instead of physically performing the row operation, you simply think of EA, where E is the corresponding elementary matrix. Now, suppose, for example, you mark the columns of A which are linearly independent. Say the I1th column, I2th column, dot dot dot, ILth columns of A are linearly independent. Now you have performed an elementary operation on A and you obtained a matrix A tilde. Again, the I1th, I2th, dot dot dot, the ILth columns of A tilde will also be linearly independent. That is the thing. So if you mark certain columns of A to be linearly independent, after performing an elementary row operation, the same columns will again be linearly independent. You probably could imagine this matrix, and you can imagine an n cross n matrix, and you may think what happens when you perform the row operation. And a little thought will convince you that this result is fairly obvious. It is indeed obvious, and we must give a very simple two-line argument. Okay, so EI1, EI2, sorry, CI1, CI2, dot dot dot, CIL are linearly independent columns of A. Then ECI1, ECI2, ECIL are the I1th, I2th, dot dot dot, ILth columns of EA, and they are again linearly independent. Okay, so what is the I1th column of EA? Take any matrix B, and I want the kth column of B. It's very easy, and that kth column of B is simply B EK cap. Rule 1, remember those 4 basic rules that we wrote down. So I1th column of EA is simply EA multiplied with EI1 cap, the unit vector. But matrix multiplication is associative. It will be E times A EI1 cap, but A EI1 cap is simply the I1th column of A, so it's ECI1. So the I1th column of EA is E times the I1th column of A. Now suppose that the new columns, or the I1th column, I2th column, ILth column, or look at the I1th column, I2th column, ILth column, or the transformed matrix. I want to show that they remain linearly independent. So suppose there exist scalars AI1, AI2, dot dot dot, AIL, such that AI1 ECI1 plus AI2 ECI2 plus dot 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 AIL ECIL is 0. Then take out the E common, E times AI1 ECI1, sorry, excuse me, E times AI1 CI1 plus AI2 CI2 plus dot 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 plus AIL CIL is 0. But E is an elementary matrix, and so E is invertible. Every elementary matrix is invertible, so I can pre-multiply by E inverse. and I will conclude AI1 CI1 plus dot 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 plus AIL CIL is 0. But CI1, CI2, CIL were linearly independent, remember? Therefore, the coefficients AI1, AI2, AIL must be 0. So we have shown that if you have a linear combination of ECI1, ECI2, ECIL, which is 0, then the respective coefficients must be 0. In other words, if you have marked the columns of a matrix which are that are linearly independent, then the very same columns in the transformed matrix will also be linearly independent. In other words, if a set of columns in a matrix are linearly independent, they remain so after performing an elementary row operations. What about the rows of a matrix? If you take exercise, suppose you've got a bunch of vectors v1, v2, vk, which are linearly independent vectors in Rn. Suppose I multiply the first vector v1 by say lambda, and lambda is not 0. Again, you're going to get a linearly independent set. If I switch two vectors in the set, after all, it's a set, so ordering is not important, and it will remain linearly independent. Now, I know what I do is I do another operation. I knock off the jth vector vj and I replace it with vj plus cvi, where j is not equal to I. This new set of vectors v1, v2, dot 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 vj minus 1, the vj has been knocked off and it has been replaced by vj plus cvi. And then other vectors are kept as it is. Then this new set is also linearly independent. Now, what does this tell you? Now let us apply this simple idea to the rows of a matrix. So if you have a bunch of rows of a matrix, say R1, R2, Rk, if they are linearly independent, then performing an elementary row operations will again keep them linearly independent. In other words, the row rank will not change when I perform elementary row operations. And we also seen that the column rank will not change when I make a elementary row operation. So when I make elementary row operations, neither the row rank changes nor the column rank changes. This row rank and the column rank remain the same. So now I want to understand the relationship between the row rank and the column rank. A remarkable theorem. For any matrix A, the row rank of A always equals the column rank of A. This is a very, very important equality, and the common number will be called the rank of the matrix. Since row rank and column rank are the same, there's no need to put the word row or column. Whatever you may interpret it in whatever way you want, the number is the same. Row rank equals the column rank. So let us call K as the row rank of A. Let us call L as the column rank of A. Now I can perform row exchanges. I can exchange the rows, and I may assume that the first k rows of A are linearly independent and the remaining rows are linear combinations of the first k rows. That is, the last m minus k rows are linear combinations of the first k rows. For example, Rk plus 1, the k plus first row is A1 R1 plus dot 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 plus AK Rk. Now I'm going to perform a sequence of row operations. What row operations am I going to perform? I'm going to perform Rk plus 1 prime equal to Rk plus 1 minus A1 R1. Rk plus 1 prime equal to Rk minus A2 R2. There is a typo here. It should be Rk plus 1 prime on the left hand side. So Rk plus 1 prime equal to Rk plus 1 minus A1 R1. Rk plus 1 prime equal to Rk plus 1 minus A2 R2, etc. And if I perform these in succession, then what will happen when I do this? The k plus first row will become 0. The k plus first row will become 0. Similarly, the k plus second row will become 0. The k plus third row will become 0. So I'll perform successive row operations and I will transform the matrix A to a new matrix A tilde, such that the last m minus k rows of the transformed matrix are 0. And the A tilde is called B11, B12 dot 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 B1n, B21, B22 dot 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 B2n, etc. BK1, BK2 dot 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 BKn. So this is how the transformed matrix A tilde looks like. But we have just seen that performing a row operation will neither alter the row rank nor the column rank. So row rank of A tilde is the same as row rank of A is K. Column rank of A tilde equals the column rank of A, it is equal to L. So now we concentrate our attention on A tilde. Look at the columns of A tilde. The columns of A tilde can be regarded as vectors in Rk. Isn't that so? Because the last m minus k entries are 0. The last m minus k entries are 0. So effectively, I can think of the columns of A tilde as being vectors in Rk. The Rk is generated by how many vectors? Rk is generated by k vectors. So any k plus 1 or more vectors will be linearly dependent. So k plus 1 or more columns of A tilde will be linearly dependent. So what will be the column rank of A tilde? Column rank of A tilde cannot exceed k, because if it exceeds k, it will become linearly dependent. No, the dimension of the column space. You need a b. I mean, there can only be at most k columns of A tilde that are linearly independent. So the column rank of A tilde cannot exceed k. So the column rank of A tilde is less than or equal to k. But what is the column rank of A tilde? The column rank of A tilde is the same as the column rank of A, and that has been denoted by L. So we get that L less than or equal to K. Now we apply the same logic not to A but to A transpose. Repeat the same argument. Go through the same rigmarole with A transpose instead of A. And you will get the reverse inequality, K less than or equal to L. Obviously, the row rank of A will be equal to the column rank of A transpose. The column rank of A will be the row rank of A transpose. When I take a matrix and I take the transpose, the row and the column ranks get interchanged. But no matter which matrix it is, we have proved that the column rank is always less than or equal to the row rank. And so applying this inequality to the transpose of the matrix, we get the other inequality, K less than or equal to L, and the proof is complete. Again, I want you to realize that we have used the fundamental lemma over here, that in Rk, which is a vector space generated by k vectors, k plus 1 or more vectors will be linearly dependent. The fundamental lemma, now we are beginning to understand how important the fundamental lemma is. So it is really fundamental. So we have proved that the row rank of A equal to the column rank of A. The common number is called the rank of A. It's called the rank of A. Now what we will excuse me. Just a minute. Now I'll take a pause for a few seconds. Excuse me. Let's continue. So now there are some further results I'd like to discuss with you. Some further results, and here they are. Exercise. These are exercises. Let A tilde be obtained from A via an elementary row operation. Now here A and A tilde are square matrices. A and A tilde are square matrices. Because they are square matrices, I can talk about the determinant of A. If you perform an elementary row operation on a matrix, on a square matrix, say interchange of two rows, the determinant picks up a minus sign. Adding to a given row a multiple of another row, the determinant remains unaltered. Multiplying a certain row by a non-zero number the determinant gets multiplied by that non-zero number. So when I perform an elementary row operation on A, I get a new matrix A tilde. What is the relation between the determinant of A and determinant of A tilde? These two determinants are multiples when non-zero lambda. So determinant of A equal to lambda times determinant of A tilde when lambda is not zero. Now suppose A tilde is obtained from A by a sequence of elementary row operations. The same logic will continue. You keep applying this rule again and again, and you will get that determinant of A is again lambda, a different constant lambda, times determinant of A tilde, lambda not equal to 0. Now from here, what do we get? Suppose, for example, you take a square matrix A. Suppose you take a square matrix A and you reduce the square matrix to In, the identity matrix, through a sequence of elementary row operations. And you perform a sequence of elementary row operations on A and you reduce it to In, then the determinant of A cannot be 0. The determinant of A cannot be 0. Now recall that if you can reduce A to In through a sequence of elementary row operations, then that matrix A must be invertible. Also, if the columns of a matrix are linearly independent, then the determinant, then you can reduce the matrix to the identity matrix. Why? The columns are linearly independent. So the first column is not zero. There's at least one non-zero entry in the first column, which means that when I reduce it to the row echelon form, the 1 entry is non-zero and all other entries below it are 0. And the 1 entry can be made 1 because I can do a row reduced echelon form. Okay, now that you have got the first column to be 1 0 0 0 0 0, go to the second column in the row reduced echelon form. What about the second column? In the second column, there is a 1 2 position, and underneath the 1 2 position, there's a 2 2 entry, the 2 2 entry, 3 2 entry, 4 2 entry. Can they all be 0? Can the 2 2 entry, 3 2 entry, 4 2 entry, dot dot, can it all be 0? If all of them is 0, then the second column will become a multiple of the first column. No? But that's a contradiction because the columns are linearly independent and they'll remain linearly independent after performing elementary operations. So the second column is linearly independent from the first column. The second column is not a multiple of the first column. So among the 2 2 entry, 3 2 entry, 4 2 entry, one of them must be non-zero, at least. So again, the row reduced echelon form will have 1 in the 2 2 position. Once it has 1 in the 2 2 position, then I can use that 1 to kill the 1 2 entry. And so if you look at the row reduced echelon form, then it is 1 0 0 1, and then other entries are there. Then there are other entries. Are you convinced that if the columns are linearly independent, then I can reduce A, then I can reduce A to In. Through a sequence of elementary row operations, I can reduce A to In. That's an exercise. Yet another exercise I want to discuss. Suppose dimension of V is K. Suppose if you have dimension of V is K, and S is a linearly independent subset of V containing exactly K vectors, then S is a basis. See, for a basis, we need two conditions, right? The basis must be linearly independent and the S must be linearly in order for S to be a basis, S must satisfy two conditions. S must be linearly independent, and linear span of S must be the whole of V. Here I am saying S is linearly independent, but instead of the second condition, I am not saying that linear span of S is V. Instead, I am saying that S contains exactly K vectors, where K matches with the dimension. Then we have to conclude that the linear span of S is exactly V. In other words, you have to conclude that S is a basis. The second exercise is similar. Suppose S is a set of K vectors. Then the number of elements in S is exactly K, but the linear span of S is V. Then prove that S is linearly independent. In other words, S is a basis. So we got these two things. So the basis must satisfy two conditions: linear independence and linear span must be the whole of V. But what I do is in each of these two exercises, I'm knocking off one of the conditions, and instead of and in its place, I'm saying that the cardinality of S, the number of elements in S, is K. So then again, it's a basis. So now let us assume that you got a square matrix. You got a square matrix whose columns are linearly independent. You got a square matrix whose columns are linearly independent. Then this matrix must be invertible. Let us see why. Since the columns are linearly independent and since their number is exactly n, it will be a basis for Rn. It will be a basis for Rn. Because it's a basis for Rn, its linear span is whole of Rn. So E1 cap can be obtained from C1, C2, Cn through some linear combination. E2 cap can be obtained from C1, C2, Cn through some linear combination, etc. En cap is a linear combination of C1, C2, Cn. Stare at this equation and you will immediately see that BA equal to I. If you stare at this equation, you will immediately see that BA equal to I. So A is invertible. Conversely, if A is invertible, then the columns are linearly independent. The same argument can be reversed. And so you got to prove that if you have a matrix, square matrix, then now we can prove the theorem. Let A be a square matrix. Then the following conditions are equivalent. Rows of A are linearly independent, columns of A are linearly independent, A is invertible, and determinant of A is not zero. 1 and 2 are equivalent because row rank equals column rank, and here we are saying that both numbers are n. Both numbers are n. And so 1 and 2 are completely, the equivalence of 1 and 2 follows from the equality of row rank and column rank. 2 and 3 are equivalent is one of the exercises that we just did. 2 implies 4. If the columns are linearly independent, then I know that I can reduce A to identity matrix through a sequence of elementary operations. And the very first exercise that we did, says that the columns are linearly independent, the determinant is not zero. So 2 implies 4 is one of the exercises above. So all that I have to show is 4 implies 2. To show 4 implies 2, it is enough to show that not 2 implies not 4. Contrapositive. I prove the contraposition. Not 2, negation of 2 implies negation of 4. So what is negation of 2? Negation of 2, columns of A are linearly dependent. So if columns of A are linearly dependent, then the rows of A are linearly dependent. If the rows of A are linearly dependent, then one of the rows can be made zero through a sequence of elementary row operations. But now I am obtaining these two matrices, the determinant of these two matrices are related by lambda. So determinant of A equal to lambda times determinant of this other matrix. But the entire row is zero, so this determinant is zero. Therefore, the original determinant of A is also zero. So negation of 2 implies negation of 4. The proof of this equivalence is being established. Now this leaves one last thing called the Kronecker-Capillary theorem. The Kronecker-Capillary theorem says that a system of linear equations Ax equal to b has a solution if and only if rank of the associated matrix equals the rank of the augmented matrix. This I shall do next time. I shall stop recording and I shall stop it here.